Hello, everyone, and welcome to our Friday seminars. We are pleased to have with us today as our speaker, Dr. Subhabrata, whom I have known for a while since undergraduate when he was not a doctor. Subhabrata is currently an assistant professor of statistics at Harvard University. He received his PhD from Stanford in statistics, where he was jointly advised by Amit Gambo and Andrea Montanari. And then he also was a SPAM postdoctoral fellow jointly at MIT and Microsoft Research in New England. Uh, he has received also various awards and distinctions for his very good work so far, including the Probability Dissertation Award at Stanford and remind me, AMS Simmons Travel Grant, as well as an honorable mention and the part of Arnold Society. And yeah, and he's also a regular visitor at the Simmons Institute at UC Berkeley. So these are just a few of these awards and distinctions. He has varied interests, research-wise, spanning across applied probability, theoretical statistics, and machine learning. Some of his specific interests are in high-dimensional and non-parametric statistics, networks, and random graphs. And today he's going to tell us about some of his recent work on mean field approximations for high-dimensional Bayesian regression. Please join me in welcoming him.
Thank you so much for the invitation. Thank you, Abhishek, for the very, very kind introduction. So I'm super excited to be here and to be talking about some of my recent work on mean field approximations for linear regression. This is particularly exciting for me because there are many eminent experts in this area in the audience here today, so I'm sure I'll be learning a lot as we go along. So I started this work, this line of research actually with my collaborator Shumit Mukherjee, who's at Columbia. And Shumit, I think, visited this seminar quite recently and sort of spoke of some of this work. So I'll try to keep the overlap at a minimum with Shumit's talk. I'll survey some of that, but I'll focus mostly on some follow-up work with my student Jiazhi Chu, who is at Harvard. Okay, so, maybe I need to be closer. I can use this. Okay, so let me start with just setting up the framework for Bayesian inference. Of course, this is very well known to the audience here, but I just put it up here so that we can set up some terminology. So I think of a setting where I have data D, which is drawn from some parametric family of distributions p theta, and I'll always think of theta as a high-dimensional parameter, so it's in some p-dimensional space. Given this setting, under the Bayesian strategy, we come up with a prior pi, use the likelihood and the prior to construct the posterior, and carry out inference based on the posterior distribution, right? That's the general approach for us. Now, there are two main questions, right? The first is, okay, what are the actual properties of the posterior distribution? Like, is it giving us something reasonable? Is it efficient, and so on and so forth? And then there is a more practical question as to, okay, I have this posterior distribution, how do I actually work with it, right? So how do I actually maybe draw approximate samples? How do I approximate integrals under this posterior distribution, right? Now, for the second question, the most common approach traditionally has been to use Markov chain Monte Carlo methods. But an alternative that has attracted a lot of attention recently in statistics and machine learning is this idea of using variational approximations. So I'll focus a lot on these approximations throughout the talk. I'm introducing these to you as a computational device that can help you work with complicated posteriors, but as we go along, I'll flip the perspective. And hopefully I'll convince you by the end of the talk that these variational approximations can also be used as crucial theoretical devices that can give you a lot of insight regarding the fundamental properties of the posterior distribution that you care about. Okay, so they will serve a dual role as we go along. So what are these, what is this approach of using variational approximations? It's sort of quite straightforward. You say, okay, I have some complicated posterior distribution P of theta. I don't know how to work with it. I don't know how to sample from it maybe. So what do? I actually approximate it, let's say in KL divergence, by a distribution coming from a simpler class. Okay. And now depending on what this class script C is, in certain cases, this optimization can be carried out quite efficiently, right? And the most popular choice for this approximating class is the class of product distributions. And this particular choice and the associated variational approximation is referred to as the naive mean field approximation. Okay. Okay. So when is this a reasonable thing to do? Now, of course, you would believe that if your actual posterior distribution is roughly of a product form, then this would be a reasonable thing to do, right? So if your dependencies are quite weak in some sense, this would be, reasonable. And this is sort of the assumption that is implicitly being invoked whenever we use this approach. And this has been used increasingly in applications in modern machine learning, for example, in models with latent variables, and it really speeds up computations by orders of magnitude. But today we'll try to look at the theoretical properties of these approximations, right? When are they reasonable? So it turns out our understanding of the accuracy of these approximations is very much tied to the actual behavior of the posterior distribution as a whole. Okay, and over the past maybe decade or so, crucial work by some people in the audience and the broader community essentially has pinned down the behavior of the posterior distribution and these associated approximations sort of in a setting where there is posterior consistency. Okay, so let me talk a bit more about this first. So the starting point for this general direction is the classical asymptotic regime, right? This is our well-known regime where I have a p-dimensional parameter, p is fixed, and n, which is the number of samples, diverges to infinity. In my schematic diagram, the red dot represents, the underlying true parameter from which the data is generated. And under reasonable assumptions, in this case, it's very well known that if you construct your posterior distribution, it's consistent and sort of consistent at the root n rate, in that if you look at a ball of radius 1 over root n around the truth, that contains most of the posterior mass. Okay. And it has now been established actually fairly recently that at least in these classical regimes, the naive mean field approximation also gives you something reasonable, in that it also puts its mass around some 1 over square root n ball around the truth. Okay. Okay, so this is good, but now you say, okay, this is sort of a low dimensional regime. In modern applications, we routinely run into high dimensional problems. So what happens in high dimensions, right? Something morally similar happens if you have sort of enough signal strength in your data to have sort of consistency and contraction. Okay. So roughly what happens in this case, and the predominant example of this is a setting where you have sort of a high dimensional model, but you can assume sparsity in the underlying data generating distribution, right? So what happens in this case is that, again, in this schematic diagram, you have some data generating distribution, which is depicted by this red dot. Suppose you assume that there is sparsity in this underlying model. Depending on the complexity of the parameter space, you can now prove that basically a reasonable, if you use a reasonable prior and construct the posterior, it will put its mass on some ball of shrinking radius around the truth. But if your parameter space is more complicated, then the radius is not 1 over root n anymore, it's some other rate epsilon n. right? Okay, any questions so far? And I should say, please feel free to interrupt me, jump in with questions, any remarks. I really welcome that. Okay, so in this regime, right, when you have contraction, you can say, okay, in these regimes, are these mean field approximations reasonable? Okay, should I actually be using them? Do they perform as well as the true posterior, right? And there has been progress on these questions. I put down some of the references here, but we now understand sufficient conditions on the model and the prior, which ensure that if you look at the posterior distribution and its variational approximation, they essentially are supported on balls of the same comparable radius, right? In most generic settings. Okay? And these studies have kind of focused on regimes where there is sort of a high dimensional model with sparsity, let's say. So my goal today is to go beyond this regime. Okay, I really want to talk about a setting where the posterior distribution actually is not consistent, right? So I think of these regimes as high dimensional regimes where I have lower signal to noise ratios, so that my posterior distribution cannot really contract to a single point. It still remains diffuse, but it still contains non-trivial statistical information. So I should still be able to carry out non-trivial inference based on the posterior distribution, just that it will not be consistent, right? And I'll ground my discussion today in the context of a high dimensional linear model. Okay, so just setting up some notation here. I observe n data points, yi, xi. Yi's are my responses, these are real value. Xi's are my features, these are p-dimensional. Okay, and throughout I'll assume that both n and p are growing, and we'll see what assumptions we need on n and p and their relative growths as we go along, right? And because I want to think of a setting where there is no consistency as a whole, and I kind of want to understand what happens to the posterior distribution, I'll start with sort of the simplest setting, right? We can, I mean, one can definitely argue that this is not the setting that you would want in actual applications, and one can try to go beyond this. But for our investigations, I'll just start with the IID product prior in this case, right? So my setting is that I have beta 1 to beta p, which are IID from some prior pi. That's the model that I use. And then I see my data from a linear model. I'll also make another simplifying assumption that the variance of the additive Gaussian noise is actually known to the statistician throughout. And finally, okay, I have some assumption on the compactness of the support of the prior, but I think that's just a technical assumption. One should be able to do away with it as long as the prior has sufficiently light tails. So, for example, sub-Gaussian tails should also work here. I should make a point here that when I say that my Bayesian model has this prior, I do not mean that the data is actually generated or that the underlying parameter is actually generated IID from the prior. This is just the model that we use to fit the data. Okay? I don't make any assumptions on the actual generative model for the data as such here. Okay. Any questions on the setting? Okay. So this whether one has adequate signal or to noise ratios in the problem, this is actually captured by how we scale the parameters of the problem as we let both n and p diverge to infinity, right? And sort of throughout this discussion, I want you to kind of imagine a setting where even as both n and p are diverging, I keep the operator norm of my sample covariance matrix fixed to be order 1, right? This is what I mean when I think of a low SNR regime, right? Okay, why do I think of this as a low SNR regime, right? So imagine that you're doing like, imagine you're in a setting where p is less than n and you're just doing OLS, right? In this case, if you look at your sample covariance matrix, or if you look at the covariance matrix for the OLS estimate, that essentially depends on X transpose X inverse, right? So if the operator norm of X transpose X is held at a constant, then if you look at X transpose X inverse, then its typical entries are order 1. So if you look at every coordinate, there is order 1 uncertainty in estimating this thing. This is all the information that you have. So you cannot really consistently recover the underlying signal. And this is sort of the regime that I'll be working with throughout. Okay. Okay, so naturally what happens in this case is that if I keep my SNR at a low limit, then my posterior doesn't contract to the truth. It's diffuse over the entire space. But of course, it still contains non-trivial information about the underlying truth. So I want you to think of a setting where you have some fairly large parameter space. There is some underlying model which generates the data, and your posterior kind of is maybe peaked around that, but it doesn't really contract. It still has non-trivial mass away from this truth, right? And this is essentially now a combined effect of the high dimensionality of the problem and low signal strength, right? It's an interplay of the two which leads to this kind of a feature. And what I would like to do is to understand the properties of the posterior distribution in this case. Okay, what are the limits of inference? How well can we do? Can we still use these variational approximations? Okay, are they reasonable? These are some of the questions that I'm interested in here. Okay. So here is where I flip the perspective, right? I introduced these mean field approximations initially as purely computational approximations that can help us to work with the posterior distribution. But here and henceforth, I will tell you that these mean field approximations can actually shed crucial light on the actual properties of the posterior distribution. So the idea is as follows, roughly, right? And I'll make this precise as we go along. Suppose I have some high dimensional posterior distribution that I want to understand. Suppose I had some oracle that tells me that the posterior distribution is roughly behaving like a product distribution, right? Then I'm in luck, right? Because I can find in some sense what is the best approximation by product measures. And if I look at then, certain characteristics under the posterior distribution, I know it's as if I'm drawing a sample from a product distribution. I can analyze how that behaves, right? So that is how I will get information, and that is how I will extract information about the posterior. Okay, so this is what I want to do, and I want to identify settings where these mean field approximations can be accurate for the actual posterior, so that then I can just work with these approximations and analyze the posterior using this alternate characterization. The question is, okay, what do I mean when I say that these mean field approximations are accurate for the posterior? How accurate do I want them to be? Okay. Now, typically what happens is that I have these probability distributions on the p-dimensional space, and I have scaled the problem so that every coordinate sort of has order 1 uncertainty. So if I look at the KL divergence between any two such probability distributions on p-dimensional space, roughly I should have, the KL divergence should be roughly order p, so big O p, right? That is, something that's always true under our scaling regimes. And I'll say that, the naive mean field approximation at least is correct to leading order if this discrepancy is actually little o of p. Okay? So I'm going beyond what is always true, and I'm saying that I have like a very accurate approximation by product distributions if this minimized KL divergence is actually little o of p. Okay. Okay. We kind of, okay, hopefully I've convinced you kind of this alternate route, but you will then ask me, fine, but this seems to be like this really kind of strange way of going about the problem, because I need this oracle to tell me whether the naive mean field approximation is accurate or not, right? I need some way by which I know whether this is reasonable or not. How do we get that? And so we had some results in this direction. And I think this is what Sumit focused on when he visited, but I'll recount the result. So the advance here essentially comes from this emerging area of nonlinear large deviations in probability and combinatorics. This started in the work of Chatterjee and Dembo around 2014 and has had a lot of follow-ups, mostly in the combinatorics side. But the idea here is that if you have a linear regression model, specifically with this product prior setting that I set up initially, so I look at the matrix A. This is just essentially the sample covariance matrix with the diagonal entries zeroed out. That's what it is. And I have two assumptions on this matrix. The one that I have actually displayed here, sorry, my result is, this might be slightly misleading, so you should stop me if anything is unclear. This is essentially the assumption on the operator norm, roughly. Okay, I'm assuming something weaker than assuming that its operator norm is order 1. This is not the L2 operator norm, something like the infinity to 1 norm, right? So this is actually just assuming that I'm in this low SNR regime. This is what I started out with. The non-trivial assumption here is that I'm assuming that if I look at the trace of A squared, that is little op. And the result here is that I don't care actually much about what the relative rates of N and P are as they grow. As long as this condition trace of A squared is little op is satisfied, I have the naive mean field approximation accurate to leading order. Okay. This is essentially our first result. Yeah.
This encodes some kind of weak uncorrelatedness among the coordinates of x, the trace of A square.
Okay, so I'll come to that in a minute. That's a great question. That's what I'm coming to. Any other questions? Yes.
Surely the P-positive mean field is there to be 1 over n, then summation I from 1 to n, some factor like that to show its mean field, taking the average of every component. I don't see the operator here in any slide so far.
Sorry, so could you repeat that?
When people see the mean field, we just adding up everything, make a summation, and take the average of this.
Ah, good. Okay. I think I understand the question. Let me try to answer it, and then you can tell me if I answer your question or not. Right. So I think the discrepancy here is in terms of the use of the word mean field. I think in different communities, especially I think on the physics side, mean field is usually referred to a setting where, I think as you say, things are averaged. Every individual kind of sees an average of everything else, and that's what is mean field. Here, things are mean field specifically in the sense that I described before, that if I look at the KL divergence, that is little op. If that's the case, then I say that the naive mean field approximation is correct to leading order. And I think the genesis of this, and I think the connection to these, is that there are some models, for example, in statistical physics, where, let's say, the Curie-Weiss model for magnetism and things like that, we can talk about it more offline as well, where you have the naive mean field being correct, as well as the kind of picture you paint that every vertex or every point sees an averaged effect of everything. So these are kind of related in certain settings. But in my case, when I say the mean field is correct to leading order, all I mean is that if you look at the KL divergence between the best product approximation and this high dimensional distribution that you care about, it's little OP instead of the obvious big OP. Yeah. Okay. Okay. So coming back to Abhishek's question, what does this condition trace of A squared little OP really mean? What is it encoding, right? It's a bit of an opaque condition. So if you look at the matrix A, it's a P by P symmetric matrix. So if you look at trace of A squared, that's basically the sum of the squared eigenvalues of A, right? So you have now this matrix A whose operator norm is order 1, let's say. So you have in general P non-trivial eigenvalues. I'm telling you, square them, sum them up, you should get something that's little OP. This can happen essentially only if you don't actually have exactly order P non-trivial eigenvalues, right? This happens only if you have some approximate low rank condition where there are a few order 1 eigenvalues and the others are actually pretty small. That's when this approximation is true, right? Okay. Questions? Yeah.
If you consider random generating mechanism for your design matrix.
That's my next slide. Thank you. Okay, good. So, okay, examples. They are super important. So, yeah, this is exactly what Anirban is referring to. So, if I have assumptions on the design, what are conditions where this is true, right? So one specific example that will be actually relevant in all that I talk about for the rest of the talk is this example of Gaussian designs, right? So imagine you're in a setting where your rows are IID samples from a multivariate Gaussian distribution in P dimensions with covariance matrix some gamma of P, right? Now I put this condition that when I put the rows in, I scale everything down by 1 over square root n, and I need to do that simply so that the sample covariance matrix has operator norm of order 1. So this is my non-trivial scaling on the problem. Once we do that, it essentially turns out that okay, this trace of gamma p squared, is little o p. This condition is true mostly when p is little o n. Right? That's essentially the regime. So specifically, for example, if you're one very concrete example to keep in mind, because this will come up again and again, is that if your covariance matrix is the identity, then the off-diagonal part is exactly 0. But in that case, you have this accuracy of naive mean field as long as p is little o n. Okay? That's the regime up to which you see accuracy of naive mean field. And we'll see that it's harder to go beyond that. Something different happens. Okay. But this is sort of one example to sort of understand where these conditions are true. So roughly, if you have more data points than you have number of features, you do naive mean field without any sort of structural assumptions on the underlying model. It's not giving you anything unreasonable. Okay. There's a second question that I'd like to focus on for a bit, because this will be important as we go further along, which is, okay, suppose now I know that in my model, it satisfies this trace of a squared equals little o p kind of condition, so that naive mean field is kind of reasonable. What that means essentially is that if I look at my posterior distribution, it can be quite well approximated by a product distribution, right? The question is, how do I actually find this product distribution, right? And to answer that, I will need to introduce some notation here. So I'll go over it. Let me parse this, and please stop me if anything is unclear. So essentially, it turns out that a particular object that kind of contains a lot of information about these approximations, and that can be super useful, is the normalizing constant for the posterior distribution, right? So ZP is essentially just the normalizing constant for the posterior. And in general, it's quite intractable. Okay. Okay, there's a lot of formulae here. I don't want you to look at it much. The crucial takeaway is the following representation. This is what is going to be important. Okay. What this says is that you have this accuracy of naive mean field to leading order if and only if you have this following approximation to the log normalizing constant. Okay, and this is actually true even beyond the linear model. There is nothing specific about the linear model in this. This is actually just by convex optimization, essentially. Okay, yeah.
Are you assuming the Gaussian function on X here or?
Nothing. This is true for any A. This is actually direct algebra. Because if I write out what the KL divergence is, I am assuming, right, so I am assuming the form for the linear model to get this expression, but beyond that, I don't make any assumptions on the design, if that's what you're asking. Yeah. Okay, so the reason why, I go about in this roundabout way, I hope I'll convince you soon that this is something worthwhile and it gives you some non-trivial information, is that the point is now you have some non-trivial approximation for the log normalizing constant for the posterior. And the crucial takeaway actually is here, that if I can actually compute an approximate optimizer for this problem, then I have the optimizer in the scale divergence minimization problem. So these two problems are actually exactly in one-to-one correspondence with each other. If I solve this variational problem, I also get an approximate optimizer here. So if I have my posterior distribution, if I know it's approximately naive mean field, I should try to get, solve this supremum problem. And if I had, enough computational resources to get the Q hat, which is a global optimizer, let's say, then this Q hat would be a good product approximation to the posterior. That's why I care about this representation. Okay. Any questions on this? Okay. Okay, so here are the main takeaways. And I'll cheat slightly because I promised you a lot, but I'll shove some things under the carpet here for the sake of what I want to tell you for the rest of the talk, but I'm happy to go into this in more detail as well. But the big takeaways, the part that I presented, is that now you have some easily verifiable set of sufficient conditions on your design for the naive mean field to be an accurate approximation to your posterior. Right? That's the one big takeaway. The second big takeaway is that computationally, if you wanted to get a good approximation to this variational problem, you have this approximation to the log normalizing constant, and you should try to solve it in some sense. And if you solve it, then you will get a good approximation. That's the second takeaway. And there is a third part which I won't really go into, but I can speak more about it at the end, which is that if there is actually a unique optimizer, and we understand some conditions under which there is a unique optimizer, then it can actually give you information about law of large numbers type behavior for samples drawn from the posterior, right? This is essentially, my motivation for going into this entire approach, right? I promised you that if I have, an oracle tell me that the naive mean field is a good approximation, then I will understand properties of the posterior, right? So I told you the first part of the picture, how I can know whether the naive mean field is a good approximation. I didn't tell you about the second part of the story here, but one can make sense of this as well. Yeah.
Quick question: is there a relation between the optimizer you just showed on the previous slide,
Yeah.
and the usual evidence lower bound?
Yeah.
Okay.
They are very much related. Thank you so much for the question. Yeah, exactly. So generally, that's why I have this slide here. So the question here is that there is this very general relation for exponential families, which essentially states that the log normalizing constant can be written as the supremum over all probability distributions. And therefore, if I just restrict to product distributions, then I get a lower bound on that. And this is essentially usually referred to as the evidence lower bound. The kind of conditions that we are deriving essentially says that the gap between the actual log normalizing constant and the evidence lower bound is actually low of p, right? That's all that I'm saying here. Okay. Okay, so let me see how I'm doing on time. Okay, I'm good. So let me talk about something interesting that happens beyond this, right? So recall this setting of IID Gaussian designs, okay? We kind of proved that for the IID Gaussian design, things are naive mean field as long as p, which is the number of features, is little o of n, which is the number of samples, okay? At this point, you might say, okay, maybe you were sloppy in your analysis and maybe, you know, it goes beyond that, right? Maybe I don't even need this restriction of the relative growths of n and p. But I'd like to tell you that actually this is a fundamental barrier and something very different happens as soon as n and p are actually comparable with each other, okay? In these cases, you need to do something, you need to go beyond the naive mean field, and you need slightly different approximations to the posterior to actually understand things, okay? I'll be in the same setting, so linear model, product priors for the time being, just that now I will assume, and this is what I'll focus on for the rest of the talk, that n and p are actually comparable, and so they grow at a proportional rate. Okay, so this is essentially, okay, now for the next maybe 5 to 10 minutes, I'll try to present a conjectural picture of what happens for these posterior distributions. A lot of this comes from statistical physics. So this is not completely rigorous in a mathematical sense, but physicists have very, very precise techniques to make, you know, really detailed predictions about these models that turn out to be true in most cases, okay? So what I'd like to do is to try and describe this conjectured picture to you, and I'll finish with some preliminary progress that we have in understanding this conjectured picture. But what I'll tell you in the next 2 slides, this is not rigorous math, okay? But what is the conjecture? The conjecture is that if n and p are growing proportional to each other, if you now look at this log normalizing constant, this is no longer given by the naive mean field approximation that I had described to you 2 slides back, okay? But it is expected that the representation is kind of similar. So this y minus xa squared on 2 delta, this term came up. This is just the log of the likelihood. The third term here is essentially the KL divergence. This also came up. The surprising thing is this third term, okay? The interesting term here is this third term that has come up. And this is supposed to come up purely because of dimensionality effects. This is supposed to come up precisely because the number of features p and the number of samples n are now comparable to each other. This is how it's showing up. So it's rather interesting that it's supposed to have this, you know, very neat form, even though it comes out of, you know, a lot of high dimensional effects. So there is some averaging that happens, and this is supposed to capture what happens here. Right? So this particular term is often referred to as the Onsager term or the Onsager correction in the physics literature. Let me talk slightly about the history of where these things come from. So this idea of deriving these approximations to the log normalizing constant for these high dimensional probability distributions, this I think originated in the studies due to Thales, Anderson, and Palmer. all of them very well-renowned physicists. I think both Thales and Anderson received the Nobel Prizes in physics, not for this line of work. But their studies, they were trying to understand these so-called models for spin glasses. And their studies actually predated the more well-known work of Giorgio Parisi, who actually received the Nobel Prize in 2021 in physics for his work in this area. Okay, so there was a lot of attention that was focused on this, and it led to a lot of very interesting approaches. And what I'd like to convince you is that these techniques can actually give us new insights regarding statistics models that we care about as well. Okay. Okay, so what are these models, and why are these techniques from physics naturally relevant? So if you look at any formulation of statistical mechanics, then it naturally involves the study of high-dimensional probability distributions. That just comes out naturally from the formulation. And so it is sort of not surprising that the techniques that are developed there to study these distributions in turn can be useful if I want to study a high-dimensional distribution now coming up in a Bayesian context, right? These are morally same or morally comparable objects. So the techniques turn out to be kind of transferable. And there has been a lot of focus recently in kind of filling in these connections. But what is sort of the second part of this conjectural picture? So it goes beyond just the representation for the log normalizing constant. What is actually supposed to happen is that if you look at this particular formula, this is supposed to be, this is some optimization problem in high dimensions over a vector A that is, in p-dimensional space, every coordinate is between -1 and 1. Okay. What is conjectured is that if you forget this representation, if you just look at this formula, think of whatever is in the parentheses here as a loss function, optimize it, get the global optimizer. The conjecture is that there is sort of one dominant global optimizer, and that global optimizer should have Bayes optimal performance in this setting. That is kind of the bold conjecture that comes out of this entire approach. Now this is still tricky because, I have some loss function, but this is generally a non-convex loss. So how I should optimize it is unclear. Whether it can be optimized in polynomial time is unclear. But the conjecture at least is that if I can optimize this, this will give me a good statistical estimator. Okay, so understanding this entire, or formalizing this entire conjecture has multiple steps. One first needs to understand, is this, there's one side of the conjecture which is that this representation is true. There is a second side which is, if I actually do this optimization, do I get a reasonable estimator out of it? And there is a third computational question, can I actually optimize it in reasonable time? So there are multiple, there's a gradation of these questions, right? Okay, let me pause here for a minute to see if there are any questions regarding what the conjectures are actually. Any questions regarding the differences between this one and the naive mean field approximation? Yeah.
Usually in this situation, you have OP running around, but when you want to implement, there is also a constant C hidden in these bounds. What do we know about those in high dimensional situations?
So, great. So generally, I think what the hope is that at least in this case, because I'm assuming that the number of samples and the dimensions are growing proportional to each other. So ideally, when I have this little OP term here hiding the constant, what I mean is that this little OP term should not have any dependence on N and P anymore, right? Now, if you ask me, can I write down a constant? No. Usually these methods only give you things up to these additive errors, which with these, formally the results would be like you divide the left-hand side by P, the right-hand side by P, take the difference, it will converge in probability to 0 or something. But yeah, there's at least, I mean, I would say that if you care about just the statistical implementation, right, then you don't really care about whether this representation is true or not, right? You would take this estimator in its own right and you would study its statistical properties. So then you don't need to care about the little OP term as much. But I start with this because in some sense, it's the first step in understanding this entire conjectured picture. Okay. Okay. Let me check the time. Okay. Let me skip over this slide. I'll come back to this in a bit. It's sort of about, you know, how do you even make, like, how do physicists come up with these, you know, approximations, right? How do they come up with these predictions? Why is there this log term that comes up? How do I understand it, right? I told you at the start that this is not very rigorous math, but then there is still a very sophisticated and principled approach which gives you these predictions. It's not, you know, some crank that one goes about. There's a very systematic approach, and I can talk more about this. But what I would like to finish with is some preliminary progress in understanding these conjectures. So what I will do is that I'll change my prior, okay? So instead of having a product prior, I will consider a uniform spherical prior on my regression coefficients. And I will also assume, so I'll make a number of strong assumptions here. I'll also assume that the data is actually generated from this model. At the moment, I need to make this assumption. So it's a well-specified model. And I also need, so this delta is the variance of the additive Gaussian in the linear model. I need this to be sufficiently large. Okay, this is a technical requirement. I can talk more about why I exactly need this. But what I can at least tell you formally at the moment is that if I look at the log normalizing constant in this case, it has exactly the kind of representation that is conjectured in this Furless-Anderson-Palmer approach. Specifically, you see this log term coming up. Okay, so it kind of sheds some light as to why you have these correction terms when n and p are proportional and comparable to each other. Okay. And okay, so some terms look a bit different. I mean, this log 1 minus norm of a squared on p term looks a bit different, but you can kind of interpret it as the KL divergence term. Its form changes because the prior changes, but these are roughly comparable. This is your log likelihood. The interesting term is the third term, and you see this log term come up. Okay. Okay, so let me give you a very quick kind of intuition regarding why this term at all comes up and what is happening here. Okay, so the interesting thing here, okay, so I have this high dimensional sphere, right? And I have, you know, when I get my normalizing constant, I have to integrate over the surface of the whole sphere, right? What I can do is that if you give me any vector A, which kind of is here inside this solid ball, I can kind of draw this plane that is orthogonal to this vector, and it cuts the sphere at some place, right? And then I can basically look at this kind of slice that I get exactly out of this, you know, intersection of the plane and the sphere. And that essentially looks like a sphere in one lower dimension, right? And its radius is exactly 1 minus norm of a squared over p. And essentially what happens is that, of course, to get the normalizing constant, you have to integrate over the whole sphere. You can always lower bound it by the contribution coming from this entire area, right? That's always a lower bound for any A. And essentially what we show is that the non-trivial correction term essentially comes about when you actually integrate things roughly on this band. This is the geometric construction. And this kind of sheds light as to why this doesn't show up when p is little o n, because in that case, this is actually very small. When you have the dimensionality effects kick in, this is essentially what shows up, and you have these terms that now should come in. Okay, so that's sort of my rough intuition as to why you have these corrections showing up in this case. The log term or the form of the correction is very much dependent on the fact that you have like a Gaussian design. So it essentially depends on the distribution of singular values or eigenvalues of the sample covariance matrix. If that changes, this precise form will change, but the mechanism essentially stays the same, I think. Okay, let me skip over the upper bound part. Of course, as I described, I mean, this is just the start. There are, I think, the more interesting statistical questions, which is, I gave you this, max over A kind of a representation. That's what I'm supposed to optimize to get a reasonable statistical estimator. So does this work in the context of linear regression? I don't know yet. And there are questions about the actual optimization of this non-convex function. Is it well behaved? Can it be optimized? And of course, there's a question, right, that in practice, we don't quite implement these more complicated procedures, right? Most of the time, we just implement the naive mean field approach. So there is a question like, how much do you gain, right? Like, okay, this is supposed to give you the base optimal performance. What is the optimality gap if you just used the NMF solution in this case? So that's, I think, another question to be explored. I should say that there has been some progress in this general direction in the context of low rank matrices observed with additive Gaussian noise. So there is work by starting in the work by Ghorbani et al. That's a non-rigorous paper. Okay, that's sort of a non-rigorous paper. But then the rigorous study started in the paper of Fan, May, and Montanari, and then there's a follow-up, at least now I think 2 follow-up papers by Celentano, Fan, and May, who studied this approach in the context of low-rank matrices observed under additive Gaussian noise, and they can kind of prove things rigorously in this case. So they focused on the case where, I take this loss function, I optimize it. They prove that you can optimize it in reasonable time in many cases. It does lead to a Bayesian, a base optimal estimator, at least in these settings. But the techniques I feel so far are still kind of tied to this specific setting, so it doesn't directly imply anything in the context of regression models. So there are, of course, other directions to explore, going beyond linear models, models with latent features. In practice, people use more general priors, hierarchical with dependence, and of course, sort of these algorithms that try to optimize. So there's a lot to be done, I think. And with that, I'll stop. Thank you so much. Time, right?
Yeah.
Okay, good.
Thanks, Subhabrata, for the nice talk. I'll open this up for questions.
So can the right-hand side that you have within the parent be interpreted as like the optimized elbow with respect to some non-product distributions?
Okay, that is a great question. I don't think so. I mean, the connection that I did think about this for a while. The connection, and this is what I had on one of the slides. So the way this approximation actually comes about is that it comes from this so-called beta approximation. So the idea is that when I approximate this distribution by a naive mean field, I assume that there is no dependence. Everything is kind of independent of each other. The beta approximation is one step up. So I assume there is dependence, but this dependence can be encoded roughly in the form of a tree. And then if it's a perfect tree, then there is a way to calculate, low dimensional marginals to get like log normalizing constants by essentially doing dynamic programming or belief propagation. What is done in these cases, and this is the physics approach, is that if you look at the actual dependencies in the high dimensional regression case, it's a complete bipartite graph. So there's a lot of loops. It's definitely not tree-like, but the dependencies are roughly weak. And there's supposed to be some kind of central limit approximation that comes about because you're averaging many things, going back to the mean field kind of approximation. And that essentially is supposed to lead to this kind of approximation. So this formula essentially comes from the beta approach with this additional mean field kind of approximation step. Yeah.
And for this linear regression, high-dimensional regression case, I wonder in practice when people can use raw approach and or when it's the time to use the like the Bayesian variable selection, like the gauge sampler in that case. And can you please comment when to use your approach and when to use the other approach?
Oh no, so I think right. Okay. So the question is, okay, is there any from all that I described, is there any practical suggestion that comes out regarding the two approximation strategies, right? So I think they're slightly incomparable in that I think it is, I don't want to say that. Okay. So I think this is true that if you wanted to use, let's say, some MCMC kind of approach, right? From a theoretical perspective, you would want rigorous guarantees for these algorithms, right? Does it mix in polynomial time? Does it give you an approximate sample and things like that? So that doesn't really come out of what I described here, right? What it tells you is kind of a meta result that if you could optimize it, you would get a good approximation, you know, you would get a good estimator, let's say. But as I emphasized, to completely kind of advocate for this approach, one has to actually even prove that you can optimize this in reasonable time. So that's supposed to be the case, but it's not completely clear whether it's always possible or not. But at least it gives you insights into the properties of the posterior, and it seems to work fairly well. We've tried at least the naive mean field approach recently in the context of linear regression. If you have a reasonable initialization, it seems to be getting you good solutions. That's, I think, the usual observation in all the empirical applications of this method. So, but yeah, so there is some gap there, but hopefully they can be filled in.
So you told that you are going to speak about the properties of the estimator you will find if you do the optimization. But I was wondering that even when in the proportional regime, like P by N goes to alpha, and suppose the conjecture does hold and can optimize everything. So what will be the difference in the properties of the estimators, like when P by N goes to 0 and P by N goes to alpha? I mean, what should I be using for the class of dimensionality?
No, so the difference essentially is that if P by N is actually going to 0, right, then you don't need this more complicated formula. You can just do naive mean field and it will give you the right thing, at least in the IID Gaussian case, right? What I'm saying is that if P and N are proportional, then naive mean field actually is not supposed to give you the Bayes optimal estimator, whereas this more complicated estimator is supposed to be Bayes optimal. Now, from a practical perspective, there is a question, okay, what is the gap, right? Maybe this one has performance 0.99, the other one has performance 0.98, then okay, you didn't really gain much, right? But that has to be quantified. Yeah.
Is there any connection for the quantum for with the approximate message passing approach?
Yeah, they're very much connected. They are essentially two sides of the same coin. They are very connected. They are, so one can sort of see approximate message passing as an iterative approach, which is trying to optimize this objective. Okay, so they are very much related. There's a reason why I kind of was talking about this particular approach and not approximate message passing specifically in this case, and that's related to sort of whether approximate message passing can get to the optimum in reasonable time. This is sort of slightly more general because you don't need to follow approximate message passing if you know this, right? You could optimize this by gradient descent, stochastic gradient descent, any of these, right? So it seems to be slightly more general, but they are, I mean, the approach to derive them are very much closely related.
Are there any other questions?
So this is a clarifying question. I have missed it, but you mentioned the low rank plus parts, from where is it that the parameter is low rank plus parts or something else?
Oh, so the model, I think this was towards the very end. So one setting, for example, where people know this kind of approach really works is, suppose I give you a matrix M, which is, let's say, a rank 1 matrix plus additive Gaussian noise. And I want to recover this spike. And so let's say the entries of spike VI are IID, let's say, plus Rademacher with probability half. In this case, there has been considerable progress recently in understanding that in this regime, if you actually do the analog of what I described, it gives you Bayes optimal performance.
Any other questions? I had one, but I'll ask you later because you're right.
Okay, yeah, I don't want to. Thank you so much.